In the previous lectures, we have shown how many different machine learning techniques can be implemented with simple neural architectures. Most of these methods were supervised learning methods. In this lecture, we will examine an unsupervised learning method, which is singular value decomposition. We will show how to implement singular value decomposition with a simple autoencoder. To understand this lecture, you require some amount of background on singular value decomposition. Even though I will try to make this lecture self-sufficient by providing the necessary definitions, it is best appreciated if you already have a certain amount of background on singular value decomposition. So I would recommend that before getting into this lecture, if you don't already know singular value decomposition, you can perhaps visit the section on singular value decomposition in my data mining book and then come back to this lecture. So let us first start with the definition of singular value decomposition. Truncated singular value decomposition is the approximate decomposition of an n cross D matrix D into three matrices Q, sigma and P. So essentially you can represent it as a product Q sigma P transpose, where Q sigma and P are n cross K, K cross K and D cross K matrices respectively. Now these matrices have certain properties. So the columns of each of P and Q are orthonormal. By that I mean that the columns are perpendicular to one another and each of these columns have unit norm. Furthermore, the matrix sigma contains non-negative entries and it is a diagonal matrix. The optimization problem for singular value decomposition is to minimize the sum of squared residual entries in D minus Q sigma P transpose. By doing this, you ensure that D will be approximately equal to Q sigma P transpose. Now, this type of decomposition essentially creates a compressed version of the matrix D, like all unsupervised learning methods. The reason for this is that the value of K that is used is typically much smaller than the minimum of N and D. And therefore, the total number of entries in the matrices Q, sigma and P will be much less than the N cross D entries in the original data matrix D. And it is because you use a value of key K, which is typically much smaller than the minimum of N and D, that you can never exactly replicate D by using this decomposition. That is why it is referred to as truncated singular value decomposition. Now, if you set K to the minimum of N and D, you can actually obtain a zero error decomposition, and that is the standard form of singular value decomposition. Here we will focus on truncated singular value decomposition because that is the way to perform dimensional reduction of the data set. Now, this three-way decomposition is not particularly convenient when we are trying to use an autoencoder. So let us look at a two-way decomposition. This is essentially a relaxed and unnormalized definition of SVD. And you can actually derive three-way decomposition by using this definition. So in the two-way definition, you want to decompose D into two matrices rather than three matrices. So you want to find an N cross K matrix U and a D cross K matrix V such that D is approximately equal to U V transpose. And the way you can enforce that is by minimizing the sum of square entries in D minus U V transpose. So, one interesting property of this optimization problem is that at least one optimal pair U and V will exist such that the columns of U are mutually orthogonal and the columns of V are mutually orthogonal. However, there will also be other alternative optimum solutions in which the columns are non-orthogonal. Now, let's focus on the optimal solution in which the columns of U and V happen to be orthogonal. You can show that this two-way factorization can be converted into the three-way factorization of SVD, which was shown in the previous slide. And in fact, I will leave this as an exercise that suppose you are given U and V with orthogonal columns, how do you find Q, sigma and P such that the product of U and V transpose is the same as Q sigma P transpose, such that Q and P have unit norm columns and sigma is a diagonal matrix. The way to show this result is by pulling out the normalization factors from U and V in the diagonal matrix. Now, one interesting question is that this optimization problem also has alternative optimal solutions in which the columns of U and V are not orthogonal. So what you can show is that even for those solutions, even in the cases where U and V have non-orthogonal columns at optimality, these columns of U, for example, or the columns of V, for example, will always span the same subspace as the orthogonal solution at optimality. So they'll have the same objective function, and the subspace they will span, the k-dimensional subspace they will span, will be the same in both cases under certain reasonable assumption on the data matrix. Now, singular value decomposition is a dimensionality reduction method just like any other matrix factorization technique. So essentially you are factorizing the matrix into two factors U and V transpose. Now let's interpret this from the perspective of your training points which you will be using in your autoencoder. So the end rows of D contain the end training point. These are the points that we will feed into our autoencoder. The end rows of U contain the reduced representations of the training point. So ideally we want our hidden representation. So every time you feed a row of D, you want the corresponding row of U to appear in the hidden representation of your autoencoder. And the K columns of V, they contain the orthogonal basis vectors. So here I have shown the autoencoder architecture of for SVD. So here what you can show is that if you use just a simple three-layer architecture, here we are counting the input layer as the non-computational input layer as a layer. So you really have two computation layers, a hidden layer and an output layer, and all the layers are linear. So in this case, the output of this layer can be shown to be the rows of the matrix U if the input layer are fed the rows of the matrix D. Now the weights of the decoder, they contain the matrix V transpose. Now you can see that since there are K units in the hidden layer and there are D units in the output layer, the matrix V has to be a D cross K matrix. So the V transpose is a K cross D matrix. So you can now, since the operations of a neural network are essentially matrix multiplications, you can see that the outputs of the output layer will be obtained by taking the hidden layer activation vector and multiplying it by V transpose. Now essentially the output layer will contain the rows of U V transpose. Now this is exactly the form of factorization in SVD. The other point is that in this autoencoder, we are using the sum of squared errors. So by using the sum of squared errors between the input and output over the entire training data, we are essentially optimizing D minus UV transpose, the sum of squares of these entries. And this is exactly the same objective function as SVD. Now note that if you use this architecture with an autoencoder, the learned weight matrix, the decoder weight matrix, it may not turn out to be one in which the columns of V are orthonormal. This I mentioned in the previous slide that SVD has an infinite number of alternate optima, and most of them actually do not have columns of V which are orthonormal. But even in that case, whatever V that you find in that case, you can show that it will always span this D cross K matrix. If you look at the columns, the K columns of this matrix V, you can show that the subspace spanned by the columns of V will always be the same as that found by the optimal solution of SVD in which the columns are orthonormal. Now, is there a way in which one can enforce the columns to be orthonormal by using an autoencoder architecture? Now, let's go back to this architecture over here. You can see that the encoder weights are denoted by W transpose and the decoder weights are denoted by V transpose. So far, I have not enforced the encoder, any kind of relationship between the encoder weights and the decoder weights. So what are these encoder weights? One of the things that can show that the encoder weights, the optimal for any particular fixed value of V that you find, the optimal encoder weight is given by the pseudo inverse of this matrix V. And in the book, actually, I have an exercise to this effect, which actually kind of gives you the steps in order to show this result. That's exercise 14 in chapter 2 of the book. Now, if you tie, one of the things that you can show is that if you enforce a constraint on the encoder weights, that means that if you tie the encoder weights W is equal to V transpose, then the columns of the weight matrix V will become mutually orthogonal. And this is actually fairly easy to show if in the equation W is equal to V transpose V inverse V transpose, if you substitute W is equal to V transpose, and then you post multiply both sides with V, you can show that V transpose V is equal to I, which is possible only if the columns of V are mutually orthonormal. Now, this is exactly SVD. Now, tying encoder-decoder weights does not lead to orthogonality for other architectures, other general autoencoder architectures, but this is a common practice anyway while building autoencoders. Now, so far we have only shown a simple example of a linear autoencoder. Of course, we can implement that using SVD. The case in which autoencoders are really useful is when you have a lot of structure in your data. So for example, if you have a lot of nonlinear structure in your data, here I have shown an example of a spiral shape of the data distribution. Now, it's a three-dimensional data distribution, but it's impossible for SVD to find any kind of reduction which is in less than 3 dimensions and not have a large amount of error. However, if you use an autoencoder, which is a deep autoencoder with nonlinear activations, you can actually obtain an embedding of this data set in 2 dimensions. So I have shown that on the right hand side. Now, this kind of nonlinear embedding can also be obtained by using some other dimension reduction methods like, for example, isomap, which are used in traditional machine learning. However, autoencoders have some advantages because even for nonlinear dimension reduction techniques, they are easier to use for out-of-sample points, which are sometimes more difficult with traditional machine learning techniques to use them for out-of-sample points. This brings us to the other question about the cases in which it is more useful to use techniques like autoencoders over traditional machine learning techniques. If you have data which doesn't have a lot of structure, that means that you can actually use SVD. It just has linear structure, but it has a lot of noise. Then you're better off using a traditional machine learning technique like SVD. On the other hand, if you have data which doesn't have too much noise, but it has a lot of rich structure, so for example, like image data, then you're better off using techniques like deep autoencoders with a lot of nonlinearity.